Hello, everyone. Welcome back to the Geek Nighter podcast. I am your host, Keval Apte, and today I have Matteo with me from StreamNative, and we are going to talk about Apache Pulsar, which is a very popular streaming platform, messaging platform, and we are going to dive deeper into how all of that works, what is the architecture, and how does it support multi-tenancy, tiered storage, and some of the other amazing features. We're also going to compare it with other technologies and give you sort of an idea of when to use Apache Pulsar and what can you achieve. So with this, welcome Matteo to the episode. I'm really happy to have you. Let's start with a little bit of introduction about yourself and what you do.
Sure. Thanks. My name is Matteo Merli. I'm a CTO in StreamNative, which is a company that provides services and products around Apache Pulsar. And I was one of the co-creators of Apache Pulsar back in the day when I was at Yahoo. I was there for 7 years. And we started the project and we kind of like get it to production. Then we open source it, and then we got it into Apache Foundation. And then we started a company around the project to commercialize the technology.
Awesome. You mentioned a bit about how it was formed in Yahoo and created and then open sourced. Let's talk a little bit more on what was the problem you were trying to solve at Yahoo and how did Apache Pulsar came to birth?
Yes, so it came basically at the conjunction of two different main requirement realization inside Yahoo. Essentially, there was two trends. One was that each product was trying to use more and more messaging systems. There were like so many teams between different products like mail, finance, fantasy sports. There was like hundreds of them, and each of them they had some messaging requirement, and they were using either RabbitMQ or Typico or any other ActiveMQ a lot, and in some cases Kafka, and all these teams were deploying their own instance of say a 3-node cluster or 10-node cluster, and it's easy to get started. The tricky part is to maintain the system reliably in production, right? And what to do when capacity is exceeded? How do you perform any operations? And these were like all product teams, so their job is to build a product. It is not to manage the infra. So this was the first angle of requirements. The second one is that we had huge platforms like these databases or log collection systems or like huge metrics databases that had a lot of data collection and data streaming needs, and there was no good solution out there at the point. So we were in 2011-12 when we started looking at it, and there was basically Kafka also was really at the very beginning. There was no data replication. The data was not f-synced. It was missing a whole bunch of stuff. So we started with this project and essentially to unify both use cases, like from the huge platform to a small pub sub use case, and bringing that into a single platform, and bringing that in a way that we could have a multi-tenant cluster that could work for the entire Yahoo. And therefore, we can have a small team of SREs that maintain that system that knows the internals in and out, and product teams can just on board, right? Can just go on the portal, get the permissions, the capacity is already there, the system is already provisioned to have extra capacity. So it's like this 5 minutes to production model without having to understand any of the problems that at the infra level. So that was the main gist. And because we had this such variety of use cases, one interesting point was that we tried to also, since the beginning, we tried to think about from the high throughput platform level with the high scalability in mind, like many topics or like high throughput on a single topic. And so all the horizontal scalability, but as well as we had many use cases that basically we were using like almost complex features of ActiveMQ and RabbitMQ, which like this system, they're very feature rich, and developers really love all these kind of possibilities. But they're a bit trickier to be implemented in a scalable way. So that's like the tricky part is to, ActiveMQ provides you this feature, which is super complex and so on. How can we do it? How can we give you the same functionality, but packaged in a more scalable way, like removing the things that you don't need and that prevents the scalability part.
That does make sense from an organization point of view. And you mentioned a couple of very interesting points there, like multi-tenancy and having large number of topics and being horizontally scalable. We are going to get slightly deeper into those, like how it is done. But I am curious to understand some of the basic concepts that are involved in Apache Pulsar, right? So I'm coming from more from a Kafka background, right? We talk about topics, we talk about brokers, we talk about clusters, partitions, and how things are done there. What are some concepts, like basic concepts, that when we talk about Pulsar, one should definitely know?
So you have the same concept. So Pulsar has topics. Topics have producer, consumers, and the topics can be partitioned or not partitioned. That's one difference. Kafka is always partitioned. Pulsar can be partitioned or not partitioned, and a partitioned topic is just the composition of multiple non-partitioned topics. That's very simple there. The main difference from like user perspective is that in Pulsar you have concept of subscription, which is similar to consumer group in a way in Kafka, but subscription is a durable resource in Pulsar, and that is also tied with data retention. So in Kafka, you basically only have the time-based data retention. Right? You configure your data retention to 3 hours, 6 hours, how many hours you can store, but you have to store the data always for this amount of time. In Pulsar, you can do that. We have time-based retention as well, but we can also do the retention based on the subscriptions. Imagine that your consumer application is typically very fast, and when it's consuming and is acknowledging the messages, it moves forward. And if you have consumed everything, basically we can delete your data, unless you want to keep it around for some reason, right? If you want to be able to roll back. But in many cases, people don't need that rollback capability, right? Therefore, this is important, especially like in the context of multi-tenancy, right? Because if you can get rid of the data, you might have not one consumer, but maybe you have like 10 different applications and with different use cases, or hundreds. And you don't need to keep, say, 1 day worth of data for each of your 100 applications, right? That would be a huge amount of disk space. Instead, you can delete it as soon as it's consumed and processed. But if one of them has an outage, maybe, okay, application one has an outage and might be taking a few hours to fix that outage, we can keep the data and use in the entire cluster for them, right? We don't need to have always, say, 12 hours, 24 hours of data retention, but just when it's needed.
That makes sense.
And so that's one additional point there. Also, there are multiple types of subscriptions. So in Kafka, you only have consumer group, which is one single item with one active consumer per partition. In Pulsar, basically, you have the multiple types. You have similar model as Kafka, like a failover with one active per partition, but we also have different ways to consume data. For example, like we have a shared subscription, which is basically like a queue, round-robin distribution across all the available consumers with no ordering guarantees. And then we also have a hybrid mode, which is a key shared, which basically give you the per key based ordering, but you can add as many consumers as you want on a single partition. So that makes it much easier to scale up your processing, and with or without the ordering requirement.
Yeah, okay. So the basic concepts stay the same, but there are some additional concepts or features, so to say, which makes it more
Yes,
flexible from the usage point of view. So if I don't want to keep the data, I can configure it that way. And if I understand correctly, so based on each subscriptions, the data can be deleted. And I guess it depends on the slowest subscription, right? And
correct.
okay,
Yes,
so the slowest one needs to catch up, and then as soon as it is done, you just delete the data, and that makes it
yes,
more dynamic, and you don't have the topic level retention for the data, and that makes sense. So I guess we'll get a little bit more deeper into understanding subscriptions and how they help other than retention. But let's start from the high level architecture. I was going through the documents and understood that there, of course, there is a zookeeper involved for consensus, and there's something called bookkeeper, and which also uses rocksdb. So let's talk a little bit about the high level architecture. So when I look at Apache Pulsar, what are the components that I'm looking at?
mm-hmm. So as you mentioned, there are multiple components in a Pulsar cluster. One is a broker. That's the front-facing one is a Pulsar broker, and that's where all the interaction from the client are happening, right? Basically, the broker, it is your serving tier. It handles all the interactions, all the authorizations part, all the dispatching for the consumer. It does all the caching and so on. Bookkeeper is the storage layer. So that is the basic difference in the architecture between Pulsar and Kafka and others. So you have these two tiers, and one might think that, oh, why do we have two? Is this too complicated? Is it too much resources? In reality, the amount of resources, it doesn't matter between the one or two tiers. But having these two tiers gives a lot more flexibility. When we speak that Pulsar is cloud native enabled, it mainly comes from this architecture. And if you look at it, basically all the new databases like cloud native, like from Snowflake on and all this stuff, basically they're all based on the idea of decoupling the processing and serving from the storage part. Like in Kafka, one of the main issues is that you have a partition is tied to one broker, essentially, right? So you have this data locality, that data is strongly attached to one single node for one single partition. And that makes that the size of one partition cannot exceed the disk size of one node. That's one limitation. If you fill that up, that's it. The other one is that if you want to just add more capacity, you can just do it like that. You add more brokers, but now you have to do like this rebalancing, this partition rebalancing, which is a hugely pain. And for everyone that has done it understands that, because when you do it when you are like out of capacity and your system is already almost at capacity, and now you have to copy terabytes of data from one node to another one, you made as well like a very easily trigger, go over the edge and take the cluster down. Essentially, that's very common. So the first part there is that having these two tiers, basically we are able to decouple where the data of a topic is located from the actual nodes, machines, or disks. And I don't have visualization here at hand, but the idea is that, first of all, for us, one single partition, it is not just partition on the partition based on keys, but it's also partition based on time. So essentially, a single partition, it is composed of multiple segments. It is a list of segments, essentially, right? And each segment is basically a bookkeeper ledger, and each of them is independent from the others. So what happens there is that even if you have, say, one single partition in your cluster and you have 100 nodes, you can fill up all the disks on the 100 nodes, because all these segments are basically allocated in the entire cluster. So even if it's a single topic, a single partition, it doesn't matter, right? And the other advantage is that if you are out of capacity in the storage layer, you can just add more storage nodes, and new segments will be allocated gradually in the new nodes. So it's very convenient. We can do this auto scaling of the storage up and down because of that. Mm-hmm. And it comes very naturally, right? And the other one is that because the brokers, they have no durable state on them, brokers do have ownership of a topic or one partition at one point in time, but that's very dynamic. So what you can do there is that we can, if the load on the topics and the partition shifts and changes as it fluctuates, we can quickly reassign topics to other brokers. And we have a component in the Pulsar broker, which is the load manager, which basically takes care of checking the load on each broker, checking the load on all the topics and groups of topics, and basically relocates them to equalize the traffic across the cluster. And that happens constantly. And so that if you don't tip over to the resources of one single broker. And if you say, I'm out of capacity, I want to add 6 more brokers, just add them, and the topic will get reassigned there immediately without copying any data.
Interesting.
So yeah, there are a lot of advantages in having this 2-tier, and I think that people see this. Okay, 2 is worse than 1. I think that they greatly overstate the problem of 2 is worse than 1, and without appreciating all the advantages that you get, right? Like breaking this monolithic architecture. And the last one I want to get is on the zookeeper side. And Zookeeper has a very bad name during these days. I was actually, I know all the bad stuff about Zookeeper. I was like in the team in Yahoo, like when we put to production the second use case for Zookeeper. And I mean, not just Yahoo, but it was the first production deployments of across the board. And I saw all the initial pains with Zookeeper and problems and so on. The thing I would say there is that today we made all the metadata access in Pulsar. It is pluggable. And we have can be already used with etcd as well and so on. And the next step that we have been working on has been, we have implemented a new system for metadata storage and coordination, which is called Oxia. We did that in StreamNative in the last year, and it is open source as well. And we plan to basically to fully productionize in the next few months, and to make this eventually the default input for metadata. Essentially, it is like a redesign of what do we need for a scalable metadata store and coordination system. That's like the use cases that we do have in Pulsar for Zookeeper, and taking out what we don't need for Zookeeper that inhibits the scalability, kind of like, and using a very different architecture that is more suited for modern containerized environment to put in a way. Kind of like we designed with a Kubernetes cluster in mind. Okay, what can we do that using the Kubernetes as a target environment that would make life easier to build such a system. So yeah, that's what we have been busy working on there. And in the context of Pulsar, I think that the main thing about with Zookeeper has been around the metadata scalability. Like typically Zookeeper is not a problem unless you end up being in a place where you have more than 1 million topics. And that's where the new system Oxia will kick in and solve all these cases.
Sounds good. So there are so many interesting points that you mentioned, right? And you mentioned that modern databases are trying to use this decoupled architecture where they have storage separate and compute nodes were different. And that adds to dynamic scaling. And as you also mentioned in Pulsar, you can just add broker nodes as you go, and you don't have to do rebalancing because the data is stored somewhere else. And similarly, you can also increase the storage nodes if you are out of disk space, for example. So I guess this is becoming more and more popular. What is the trade-off though of this architecture? So from a general standpoint, so if I understand, there's definitely a network involved between the compute nodes and storage nodes to get the data.
Mm-hmm.
And that leads to a requirement for caching more and more data on the compute node. Is that true? And what is the other side of it? So we understand the benefits of this architecture,
Mm-hmm.
but what makes it challenging?
I try to demystify a couple of myths here that I kept hearing for many years. One is that, if you have 2 layers, then your latency is higher than Kafka, which is absolutely not true. Actually, it is lower, but for other reasons. But the main problem there is that even if you have a single layer in Kafka, if you want your data to be in at least 2 nodes, you still have to wait for the data to be at least committed on the local one and on a second broker, right? At least. Yeah. So you still have one network hop, right? And writing on 2 nodes. So that's the network hop. Second is that network hop within a single region, single AZ is typically very low. It's like in a single data center, typically 0.1 milliseconds. So that's typically not really a factor in that latency. It is more how you use the disk that determines your latency. And it is a vastly dominant factor there, right? More than the single cluster networking.
Yep.
The other part, which is true, though I think is not really important today, is that, for example, imagine that in the Pulsar case, if you want to have 2 guaranteed copies, we can just write to 2 storage nodes. And basically, your message goes to the broker will probably write to 2 storage nodes and wait for both to acknowledge. So now you have 2 copies out, right? So you have one X in and 2 copies out to do write on the storage. The broker will also cache the data in memory in the broker itself, so that consumers that are caught up will just get from the cache. So you have 2 copies out. And now in Kafka, if you do the same way, you will have 1 less network out, but there's a cache there. First of all, yes, you write 1 copy locally and 1 copy on the next one, right? So your network out from the broker perspective, it is 1 copy less. First of all, today is not really a bottleneck. Like this case, it is much become much quicker the bottleneck, and that one network copy out is typically like now you have 40 gigs TPS networks everywhere, so it is really hard to get saturated on network. And second is that if you really want to have two guaranteed copies in Kafka, you cannot just write two copies. And the reason is that the way how Kafka replication works. Essentially, you have to have main in-sync replicas set to 2 to have two guaranteed copies. But you cannot just write 2 copies of data, because if you have mean in-sync replicas 2 and your replication factor is 2, the moment you lose one of these 2 brokers, your topic is unavailable for write and reads. In order to have 2 guaranteed copies, you have to write 3 copies of data. And therefore, now you're going out with the 2x anyway. In Pulsar, with the bookkeeper, we don't need to write the 3 copies. If you want to have 2 guaranteed copies, you can just write 2 and wait for both of them. And we don't have that problem of having one extra copy to write in order to have these to sustain one node loss.
That makes sense. That does make sense. And okay, cool. So the high level architecture perspective, it's pretty clear, and where these components are used. So there's storage layer, there is compute nodes, which is the broker, and then Zookeeper is used for metadata, right? And you mentioned Zookeeper might become a bottleneck for really large scale use cases, like you have more than 1 million topics or something like that. So we are going to cover that and talk a bit more about that. But let's talk about the flow of data, right? So when you write a message to a topic, for example, in Apache Pulsar, what happens? So you talked a bit about how this goes to storage nodes and how it is replicated and all that. But let's talk a little bit more in depth. How it reaches the disk, what is all happening, how is Bookkeeper doing it, how Zookeeper is coming into the picture, and all of that from this perspective.
Okay, so in data path, Zookeeper is not involved anymore, right? So metadata is only used at specific points in time. For example, when a new segment is created and when a subscription is created, and at this point in time, right? And segments are rolled over. So whenever there is a new segment rollover, then yes, there is a metadata right there. But in the normal data plane, there is no access directly on to metadata. So basically, like a client library, the client SDK has a concept of creating a producer in the API, and that basically creates a session with the broker, right? And once you have that session is valid forever, it internally handles all the reconnections, retries, and so on, right? Both producer and consumer side. Basically the client can maintain like a queue on the client side, again, to achieve all the batching and the pipelining and all the stuff that happens on the client side, the compression, and then sends to the broker. The broker basically writes on the last segment using the Bookkeeper client SDK. And that effectively it is, Bookkeeper is very flexible at the times of writing, so you can choose your write quorum, your act quorum, like you can do, say, write 2 copies, wait for two acts. You might also want to choose to say write 3 copies and wait for 2 acts, and with the only reason for improving your latency profile. For example, like you can always ignore the slowest storage nodes, for example, in the responses, right? You can also do more complicated things like striping across multiple storage nodes, although that's more typically is not needed as a feature. But what really happens, and what really Bookkeeper is, that Bookkeeper itself is a storage system that is designed and optimized for streaming use cases, essentially, right? And so you have this concept of ledger, and the ledger is really a write-only log in a way that if the writer crashes, and the writer in this case is the broker, right? So the broker, a segment for us is a Bookkeeper ledger, which is a log. So the broker will create a new one, append entries into it. And if the broker crashes for some reason, the next broker that takes over this topic will open that log, that ledger, and it will force to close it. So it is always single write kind of model. Like, so you open your log, you write a bunch of entries, and you close it. If you crash before closing it, it is automatically closed next time you try to open it. That makes the data path very simple in Bookkeeper and very fast, because at the point the client is a single writer. It does not have to deal with multiple writers, because there is a single writer that your partition, it is served by a single broker at one point in time. So everything gets serialized in that single broker, and that single broker acts as the single writer on that log. Therefore, the client SDK of Bookkeeper has full understanding on what is committed and what is not committed.
Okay.
And in case a storage node crashes, the client SDK of Bookkeeper immediately handles that case by switching the writes to a new storage node. So basically, it is a non-event at the point. Okay, I was writing, say, Bookie 1 and 2 from entry 0 to entry 10. Now Bookie 2 has crashed or has timed out. I don't care. I will switch to Bookie 1 and 3 now, and I will replay the missing entries on the Bookie 3. I mean the one that were not acknowledged. But then basically the history of this ledger, it is that the first 10 entries are in Bookie 1 and 2. The one and from 10 on are in Bookie 1 and 3. And basically it knows about that. Handling the storage node crashes is very natural and very fast. If the broker crashes abruptly, ungracefully, it will leave the last segment to be basically unrecovered. It is open, right? So now, next time, new broker will take over this topic based on the assignment process and the load manager. It will force the recovery of that ledger, and that will basically, it is a process in Bookkeeper that kind of like try to figure out what was the last committed entry, and then it seals the ledger and then create a new one and move on.
Okay.
It's a short story. There are more things happening in the real case.
Yeah, I think that makes sense at a high level, right? So you mentioned this ledger. So it's more like a log where you just keep appending. And you mentioned something about having a single writer. So if, let's say, while it is writing to the ledger, it fails. So whenever it comes back up, it tries to close the ledger. Or can you elaborate on
Yes.
that point?
So when the single writer crashes, you cannot have a new writer on that same ledger.
Okay.
You have to close the ledger.
Yeah.
And now it is in read-only mode, essentially, right?
Okay.
That having a single writer, basically, it's a way that we don't need to run consensus on every transaction, each and every message. The data, because essentially in Bookkeeper, what you do is that you go as fast as you can without having error recovery, assuming that there are no failures.
Mm-hmm.
Now, if there's a failure, then you can fall back and do the expensive part of doing the recovery.
Yeah, okay.
But you don't have to be like pessimistic and run consensus on each and every transactions, because that's super expensive to run consensus, right? And you have lot of state to keep up and so on, right? Instead, basically, you assume that I have a single writer. This writer does not have to talk with anyone. He knows which entries he has pushed out. He knows which entries were acknowledged and fully committed. And if one fails, he can resend to a new storage node and so on, right? So he can do all this stuff very easily because he knows that it is a single writer. And therefore, you basically defer all the recovery activities just after an ungraceful crash, if needed.
Okay, that makes sense. So the client is writing data, and you also mentioned that there is a little bit of batching, of course, to make it more performant. You batch and send like a batch of messages to the broker. Then broker talks to the bookkeeper, and it uses a single writer model to make it more performant, and uses this optimistic way of writing things, so you don't have to do consensus on each transaction because there's just single writer. And of course, on rare scenarios such as failure, you have to do this expensive operation, but it's not going to be a big deal because you're gaining a lot of performance or general rights. That does make sense. And you also mentioned about having this, so once the message is there are someone who wants to read this message, right? There are, let's say, consumers who have subscribed to a certain topic, so there are subscriptions created, for example. So how does that subscription creation works, and when does that happen?
So subscription, when you create, so you have a Pulsar client and you can create producers and consumers. When you get consumers, basically you have to do it through a subscription. So you say, subscribe, this is my topic, this is my subscription name. And if you do it and subscription does not exist, you create a new one. And by default, you start at the end of the topic, right? Or you can choose to start at the beginning of the topic or any place in between. If it exists, basically you restart from where you left off. Mm-hmm. So essentially, it is like typical publish sub model, right? And so you consume, you get a message, you do some processing. If it succeeds, you do acknowledge. If it fails, you do negative acknowledge. and the message will get replayed at some point later in time. And this acknowledgement can be either cumulative, like a checkpoint offset in Kafka, or can be a individual acknowledgement of a single message and that has been processed. And from a more under the hood perspective, what happens there is that, first of all, there is a flow control mechanism between the broker and the consumer. Essentially, the consumer basically has a receiver queue, which you can set the size you want. And the purpose of that receive queue is to have more throughput so that you can, while you are processing data, the client SDK can fetch the next messages, right? And such that you never sit there waiting for the next message to be dispatched, right? And therefore, basically, the way it works is that the client advertise permits to send data to the consumer. That goes into this push and pull model. Now, in reality, push and pull can be the same. You can implement one on top of the other and vice versa. In this case, basically, Pulsar, it is really a push model because the broker is pushing data as it is available. But this push is mediated by this flow control. So the broker will only push up to what the client asked for. So you may say, by default, I want to receive up to 1,000 messages. That's my queue space in the consumer. So I will tell the broker, I give you like 1,000 permits to send me messages. Now the broker can push you up to 1,000, and then the client will, as the client consumes data from the application consumes data, it will make space in that queue, and the client SDK will ask for more, and it's going to keep that loop ongoing without any pauses. But essentially, within that limits, the broker, it is free to push the data to the consumer, and that makes the faster in general and with the higher throughput than if you have to poll. Because if you have to poll, you have to basically stop when you're done and then come back and ask for more. And if you're too aggressive, then you have too much CPU. If you are less aggressive, then you have more latency end to end. But in this case, basically, if you are done with everything, and there's a new message comes in, it will get immediately dispatched to the consumer. So typically, end-to-end latency, in most cases, it is 99% it is within 10, 15 milliseconds as well, end-to-end.
Okay. And so you mentioned briefly about the subscription creation. So you subscribe to a topic, and you basically, the broker is responsible for pushing you the messages. And the way you do it is to configure this kind of limit, like how many messages you expect. And then you have a receiver queue, which is, I believe it's just to add some back pressure and not get too many messages that you cannot handle. But it seems like the heavy lifting then is done by the broker, right? Like broker, let's say there are, I don't know, hundreds of subscribers, and each one of them have different limits of receiving. Let's say someone can process 100 messages per second, someone can do 1,000 messages per second, and so on. So there's a ton of metadata that the broker has to manage and deal with. How does that work, and how does that not become a bottleneck at high scale messaging?
All this information, it is just kept in memory, right? So it doesn't have to be persisted anywhere. So you spin up a consumer, you connect and say, I have space for 1,000 messages. And you may join, say, a shared subscription where there are other 1,000 consumers consuming from the same topic and partition. The amount of memory needed is not very high for these kind of things. And also the amount of computation is not super high. So it is not as difficult as it seems, I would say. The tricky part especially around the key share handling, because to handle like all the ordering per key within a single partition, you have to have multiple consumers, you have to track which key goes to which one, and then you have a new consumer joining, you have to reshuffle the keys. And so that's a bit, I would say, very complex, but the shared one with the round robin, it is very straightforward in a way. But yes, we have to play within this context of, you can have different consumers, even within the same subscription, you can have widely different consumption speeds, right? You can have one, and even say one message takes 1 millisecond, next one might take 1 second.
Yeah.
And that's very common, right? But this flow control and back pressure basically makes it adapt that the broker will push only at the speed that the consumer can process it.
That makes sense. And so of course, when it has to push that message, right? So it has to get that message from the storage nodes, right? So how does that come
It,
into the picture?
so in most of the cases, if the consumers are up to date with the producer, which is hopefully most of the time, and for most of the use cases, basically the data is just dispatched from the broker memory. So the broker will have a cache configurable size based on the VM memory size. It is all kept in direct memory, so it does not affect the heap and whatsoever. But this cache basically it is what is used to dispatch to all the caught up consumers. Now, if your consumers fall behind and basically that they fall out of this cache range essentially, then they will trigger reads on Bookkeeper essentially. Now, Bookkeeper also has its own set of caches. It has a write cache, it has a read cache. On the read side, basically, it can either find it in the write cache if it was not so old data. Otherwise, it will use the read cache. And the read cache is exploiting the fact that the data it is stored in, there are intervals of sequentiality in the data, how it is stored in Bookkeeper. So we tried for each time we flash the data on the disk on Bookkeeper, we try to put the data for same ledger close together. First of all, okay, I'm going to enter a bit in the Bookkeeper storage model, but one big difference is from Bookkeeper, how it stores the data versus Kafka, is that in Kafka, typically you have one partition is one directory, and it has a bunch of files there. There are many files, and there are segments, and each segments have at least 3 files that are all M-mapped. And it is one of the main reasons of the latency issues in Kafka, and also the scalability with many topics, because you cannot have many. It becomes very inefficient to have so many open mapped files and many files in general. Right? In Bookkeeper, basically, the concept of ledger is purely logical. It is abstracted, and at the storage level, there's just big files of 1 to 2 gigabytes that stores data for many topics, many ledgers. Mm-hmm. But within these big files, there is a chunk of disk space, which is all the entries for 1 minute for one topic, for example. That means that we have at least room for some sequential data stored on the disk. And what we do is that we do like a read ahead pass, and then basically fetch a bunch of data into a read cache, and then all the subsequent read will find it in the read cache.
Okay.
Yeah. So there are multiple levels of caches there, essentially.
Okay. Yeah, that makes sense. And I'm trying to also compare it with my understanding of how Kafka works, and I see clear differences in what can be the benefits of this architecture. And again, separating the compute and storage also gives you this unique ability. One is to support as many topics as you want. And so is this the only reason Pulsar is able to support high amounts of topics? So it says something like 1 million topics. And I guess with Kafka, it's not really possible. So what are other features of Pulsar that enables it to support so many like high number of topics?
I would say the first and most fundamental one is it is really the storage, right? And the fact that you don't have one file or many files per one single topic on the disk. And if you look at how Bookkeeper stores data, it is much more complex. We have basically, there is a concept of journal. Basically, like everything that goes to this Bookie node will get synced on the journal. And the journal, basically, it is a purely sequential. So everything goes on the journal and it is comes in and synced as it comes in, right? So basically, it is only interleaved. And then the data that gets written in the journal, it is also added into a in-memory write cache. And then when this write cache is full, it can be like a 4 gigs or like say every 1 minute or so. You take these 4 gigs of data and you just order it, order by ledger and enter it in so that it is sequential, and then it is written on these big files. And that's where RocksDB enters the picture. Essentially, since we have these big files that have data for multiple different ledgers and so on, then we need an index, right? And that's where the index it is kept in RocksDB.
Interesting. That's very interesting. And I was reading the website, and it talks about, so 1 million topics is one thing that it highlights. The other one is 10 milliseconds, streaming latency. So what does that mean? So give us a little bit of understanding there.
Sure. So the 10 millisecond part is that one of the main use cases for Pulsar, and it was true in the beginning and still very true today, we see it every day, is that most of the use cases are for mission critical systems, like people building applications where their core business depend on being able to publish on Pulsar. And if Pulsar is down, then, or if Pulsar has high latency, that's very bad news for them. It's there's a immediately visible impact on their user experience. So maybe someone is trying to update the page and the page is blocked until the message is published. So that's or you try to buy something or you try to do anything. So it is always like in this critical use case in which there is a lot of sensitivity to the latency. And because you're sitting at the bottom of a much longer stack, you have to kind of give SLA that, okay, 5 milliseconds, 10 milliseconds, 99 percentile, such that the upper layer can provide their own SLAs to everyone else, right? If the overall budget, say, is like 50 milliseconds, then you can't just have a 99 percentile of 50 milliseconds because then the other 5 components in the stack cannot do anything else, right? That's what typically people will come up with these kind of like SLAs, and depending on what they're building, depend on how complex is the application, they will have such requirements. So the first part, like how do I to achieve these kind of latencies and to be consistent in them? I think that's the most important part, right? And especially it is important to be consistent in all the scenarios, right? Even when there are things that are more uncommon. The first part is that so Broker will never touch the disk, right? Broker is completely in memory. There's no disk access, and that's typically and everything it is asynchronous in Broker. So all the operations are asynchronous. There are no blocking code whatsoever. That's the first part. In the storage layer, in bookies, to guarantee that kind of latency, the important part is the journal. So the journal, typically you have the journal, which is a separate disk that is dedicated for this purpose, right? So that therefore you have their latency because it is not impacted by the reads or write that might be happening on your other storage device where you write the data. And that basically also that we don't use mmap files, for example, because mmap is a very nice concept and it's very easy to use. The problem with the mmap is that it's completely unpredictable, and it is based on the fact that if your data set is within the page cache size boundaries, then your access on this memory region is fast. The moment your data set grows and exceeds the RAM size, then these memory regions are not in memory anymore. They have to be paged out, and something else gets paged in. And at that point, what happens in Kafka, for example, when you have consumers that are reading all data, what happens is that the page cache gets trashed, and then the producer that was trying to append some new message, it tried to access a memory region, but that's not memory access anymore. It is a disk access. So now your thread is blocked by 200 milliseconds or 500 milliseconds, depending on the disk access time there. And it is very unpredictable because it is based on the page cache algorithm that has no idea of a usage pattern, right? Like in Bookkeeper, we don't depend at all on the page cache. And actually, we have the new version that we have. It is using direct IO directly to avoid any page cache interaction and overhead. But even with page caching in between, if you have consumers that are doing catch-up reads and reading very old data, that won't impact your latency because the latency is only gated by the journal latency.
Interesting. Okay, and that's how this upper bound of 10 millisecond is just avoiding any unpredictable latency that might happen.
Yes.
That makes sense.
And that's very important as well on the if you put that in the context of multi-tenancy. I think that many people think that multi-tenancy is easy, as in that it is just based on having ACLs and authorization and naming. But actually, the harder part of multi-tenancy is that if consumer A is doing catch-up reads and with disk, that shouldn't degrade the performance for consumer B, right? Yeah. That's or producer, right? If you have a critical user that say, why my latency is higher now? Oh yeah, because some other guy is doing catch-up reads, and that's not multi-tenancy, right?
That makes sense. I was about to come to multi-tenancy. How is that kind of tenant isolation done? So you were mentioning that if consumer A is doing a lot of reads, it does not impact consumer B. So how is that isolation done? And what are some things there that people should know about?
Yes, so there are multiple layers of isolation, right? So
Yeah.
the first one is to make sure that in the normal course of action, right, there, if the CPU in brokers is not exceeded, nothing should be blocking, and there is no like a direct blocking access to files within the IO threads that can be blocked by different users and so on. That is like a very bottom level. Like on top of that, then you have things like you might have things like quotas. For example, like you can apply quotas for ingestions or for dispatching for different topics, or even for groups of topics. Like you can say, okay, this tenant only has a quota of 100 megs per second, and basically any topic that this tenant has, it is subject to this overall quota of 100 megs per second. And that's enforced across multiple brokers
Okay.
in the whole cluster, right?
Hmm.
And then you have things like the storage quota that you don't let. If you say that this tenant is only allowed to 1 terabyte of storage, then basically it gets blocked when, or data, you can choose whether you want to stop ingestions or stop publishing or delete all data when that quota is reached, essentially. And yes, and the one further level up is that there are cases in which features and the way people use features might cause any side effects on other users. And typically that has been true like for whenever we added a new feature or like any complex enough component, new use cases that the way that they use it, it is causing some maybe like too much CPU using in the broker. Therefore, there is some CPU exhaustions there. So for all these use cases and to have a way to quickly react to any such situation, there is a concept of isolation.
Yeah.
So isolation works that basically you can quickly say, okay, these topics, just put them over and assign them to this subset of brokers. And this broker will be dedicated, say, for this tenant or for these topics and for this namespace.
Yeah.
It's like an operational tool that if you see that something is happening, you can quickly react and remove the damage immediately, essentially, from any impact on the other one, and until that proper fix can be made.
That makes sense. And avoiding with this architecture, you're able to avoid the unnecessary rebalancing when things like this happen. And I guess this would also help to quickly make the new brokers or quickly mitigate the risk on other consumers because of one consumer. Because you don't have to rebalance, you just have to reassign the
Yeah. So
service, right?
there's no data copied whatsoever. It is just that the assignment. It is just to have a rule to additional rules on how topics should be assigned to brokers, and saying that I want that these topics should be on their own because they're causing some impacts at the moment.
Interesting. And so when I create a topic or when I create a producer, so I have to assign quotas, or how does quota gets decided?
So you have different ways of assigning quotas. You can assign quotas, for example, on namespace, and that gets applied to every topic on this namespace. And these are per topic quotas, for example, for storage, for ingestions, and so on. And then there's a concept of resource groups, which is essentially a way to say a tenant can belong to one resource group, and then I attach a quota number to this resource group. So this can be done dynamically, not at the creation, right? So you can add it at any point in time, change it, increase, decrease, and so on. But there's a resource group. It works in a way that you can attach multiple resources. It can be, okay, this topic A and topic B belong to a same resource group, and this resource group has quota of 100 megs per second, and they both share the same quotas. Or can be tenant A is part of this resource group, or maybe namespace A and namespace B, all the topics that within these two namespaces belong to this resource group.
Makes sense. Makes sense. Let's talk a bit about tiered storage because that is another very important aspect of such streaming platforms. So, how is that done? And I guess having a separate storage layer also helps there a bit?
Yes. So the initial consideration we were doing, so we had tier storage like years ago already, right? It is. I think we were one of the first system to have tier storage. There are controversies on which system had it before, but that's another story. The main reason was to say Bookkeeper, it is all nice and cool. Though like if you are in a cloud environment, to keep VM up just to keep a disk online does not make economic sense, right? It is fine for short-term data, but if you want to keep like days and weeks of or month of data, that doesn't make any economic sense. So let's take advantage of the architecture of Pulsar and Bookkeeper and making sure that we have all these segments in our topic that they're already closed. So it is very clean cut point there, right? That I have a segment which is fully closed in Bookkeeper. I can take this segment and put it on an S3 and just change my pointer that is not in Bookkeeper anymore. Now it's S3, and that's it, right? That was the original idea, and we have so many use cases using tier storage today. So one thing that we have been working on in StreamNative in the last year or so has been around trying to also rethink a bit this tier storage model, right? Because one of the things that people will do is that, okay, I have 6 months of data in Pulsar with tier storage, which is cool. I want to do a full scan of this data, and I want to run a batch job with any system. And now the data it is in a streaming format, essentially, right? It is in a raw format. It is not in columnar format. So if you want to do any analytics on this data, you have it in a raw format, which is not very efficient. You have to do a full scan of the data because there is no other index, essentially, right?
Yeah.
That you can use. So one realization there, we've been working with all these lakehouse technologies like Delta Lake, Hoodie, Iceberg, and essentially basically integrating the tier storage of Pulsar such that it can offload the data on tier storage, but using the Delta Lake format. The advantage there is that now you can have your data in multiple ways. So you can have your data in streaming format, but it is also immediately available as well as in a Delta Lake format. So now you can use any batch job. You can use Spark or any other ways of doing queries using Delta Lake format, or Hoodie or Iceberg. So that's the main advantage there, because it not only uses a format which is already standardized. You can use Pulsar APIs or Delta Lake, any other lakehouse technologies APIs and tooling there to access in a batch way with bypassing competent brokers. And the other advantage is that it brings down the latency for which the data is available on the lake. So today with tier storage, essentially we do it after a few hours, but as well as when the ledgers are closed, when the segments are rolled over, which can be many minutes or even hours, right? At least using this lakehouse tier storage, what we can do is that we can have the data available there within one or 2 minutes. So essentially, like it becomes much more like near real time available in the lakehouse.
Okay, that makes sense, and it's a very important feature that many organizations are considering now, because as you mentioned, there is this cost involved and you want to get rid of, let's say, the old data, for example, but you still want to have some form of access to it. So I guess more and more adoption is expected, like for in terms of tiered storage as well. Before we end this discussion by talking about the future, I want to talk about two more things. First, about StreamNative, right? What it is and what are the use cases and where an offering like StreamNative should be used.
I would say Pulsar, it's kind of like, if you look at the feature set of Pulsar, it is really like a superset of what Kafka provides. And in a way, you can compare like a more traditional. So it's kind of like overlapping between PubSub and the event streaming, right? So we support everything that Kafka supports, but there is much more high-level functionality. If you compare with something like RabbitMQ, ActiveMQ, or all these traditional PubSub, we have all the same functionality, high-level APIs and so on, but we have it in a much more scalable way with much more strong guarantees in terms of durability, in terms of availability and operational stuff. So when you have to decide which one to use, there are multiple considerations there, right? There are performance implications, there are use case implications. I think that any use case that has like a need for a high-level API with complex routing and different ways to slice the data, if you need any like queuing model, or if you need any like a thing like a negative acknowledgement, delay delivery, or like data queues, like all these sort of features to build a complex event-driven application, I think that also provides much more than what Kafka provides today. And if you're looking for something that is, I just need to ingest these HTTP logs from one place to another at a very low throughput, anything can work. So it's not, sure, can do it, Kafka can do it. It is not that different. If any mission critical system, I would say Pulsar architecture has an advantage in the way that the availability is achieved and is offered. Especially like, if you consider that in Kafka, like you can have 100 node Kafka cluster, but if you have, say, replication factor of 2 or 3, if 2 of these brokers are down, your topic is down.
Yeah. In
Pulsar, as long as we have any 2 brokers up or any 2 bookies up, we can accept writes and reads. I mean, reads, if both copies of the data are down, reads might be temporarily unavailable until you bring up these 2 copies, but the write availability will still be guaranteed as long as you have 2 storage nodes to write on for the new data. So it is a very different write availability guarantee that Pulsar versus Kafka. And if you compare the kind of SLA you can offer on write availability, it is very different there. So there's a lot of overlap. There's also like a lot of differences in terms of use cases that are better. I would say that anything that is more suited for looking for a high-level pub sub in semantics, I think Pulsar has an edge there on having a simpler and more complete offering there. StreamNative is a company to provide products and services around Pulsar, and as I said before, and the products we have are around our cloud services, and where we do have our hosted cloud, which is a pure SaaS offering of Apache Pulsar. And we also have our BYOC cluster, which we deploy in your cloud account, and it is managed by us, fully managed both on the SaaS and the BYOC offering. And finally, we have our private cloud, which is a self-managed distribution of the same distribution that we have that we use for the cloud. And basically, that distribution comes with several like operational addition to the open source Apache Pulsar. We have Kubernetes operators. We have a lot of helpers there in terms of how we do the deployments of Pulsar clusters, how we do the observability, all the parts of like auto-scaling for brokers and storage nodes and so on, and all the troubleshooting helpers. So and then all the integrations that we have with the cloud providers, with different enterprise security and so on. Essentially, it is kind of like even the self-managed version, it is a way to get it to be much easier to get started with everything out of the box in.
Okay, interesting. Awesome. What's in the future? You mentioned a couple of things around this new component to support really high scale use cases. Let's talk a bit more about what's in the future in terms of feature set that Apache Pulsar is going to bring.
Sure. Yeah, so we started working last year on this project, which is called the StreamNative Oxia. And as I mentioned, the goal was to create a metadata serving layer, that metadata and coordination serving layer that, based on the Kubernetes semantics, that could basically have an unbound amount of metadata. So the amount of metadata, so Zookeeper, most people will know that, but basically it is a consensus system, but it is not horizontally scalable because every single Zookeeper server has the entire data set. So you can't grow it indefinitely, right? So the amount of writes per second, reads per second is limited. The amount the data set size is limited. So I do think there is a lot of very good use cases that take advantage of the fact that I can have many cheap topics. And we have it already in many production clusters that we manage for our customers. We have like many with hundreds of thousands of topics, and very easy, and it works very well with Zookeeper today. But the question is that what can we do it to like one level up, right? What can we increase if we increase this number by 10x or 100x? And the main idea is that in many cases, you like if you're using Kafka, for example, like the typical solution that would be that use one single topic for, say that our resource in your domain could be, I don't know, like a customer or a marketing campaign or something that makes sense in your business domain, right? And when you think of it, you say, okay, I might want to have the ability to see all the events for this user, like everything that is using the history of this user, for example, right? Or I want to receive only data for this user, and so on. In Kafka, what happens is that you have no way of having one topic per user. So what people will be forced to do is that you have a single topic with multiple partitions. And now, yes, one user gets assigned to one partition, so you have all the events in the order in that partition. But if you're trying to ask the question, how can I replay the data only for this user? Well, yes, you can find out the partition, but still that partition will contain data for many other hundreds of thousands of users. So now you have to do a full scan of all the data and so on. Also, you cannot have any, so you have no visibility also on how much data each user is sending. You have no metrics, no access to visibility on there. And you have no isolation between users, right? If user X is sending 10x or 100x more events than user Y, it's going to wait behind user X. And because everything is serialized there. And you have no way of applying any rate limiting, for example, right? Let's say if user X is exceeding his quota, you cannot apply the quota on one user because you have a single topic there. So there are all these limitations, right? And if you can think that I can use many topics, I can use a million topic, I can use like 10 million topics, then it becomes very attractive to have one topic per event, right? And to me, it's like going from the database table where you have no index and you have no idea. I have to do a full scan every time you want to search for something to now, okay, now I have an index. I can look up for everything from my user. And this kind of like the same performance improvement that you can get there. And you can consume from only for, if you want to consume only for one user or for a few users, or give different permission to have, say, different teams in the company might have access only to a subset of them, and so on. You can have a very fine-grained access control there instead of having the full whole of all the events.
Okay, cool. Being a Kafka user and person who has built many applications on top of Kafka, after learning about Apache Pulsar, I'm definitely more curious to learn more and, more importantly, build applications on top of it. So thanks a lot, Matteo, for this amazing overview and introduction. And we also managed to dive deeper into some of the topics. In the interest of time, we have to end this amazing session. But thanks a lot for joining us today and sharing insights into the workings of Apache Pulsar. And I'm looking forward to work on Apache Pulsar and build some applications, and more curious to learn about it, and also looking forward to the new features. So thanks a lot, and I'm sure this is going to make many of our viewers curious and try Apache Pulsar.
Thank you for the question. It was a lot of fun today. And if you have any other questions when you're going to explore Pulsar, please ping me or go communities. There is always many people very helpful there.
Awesome. Yeah. Thank you.